So welcome to Homerton College. Behind me, my name is Matthew Moss. I'm Director of External Relations and Development and Zoom expert. I would like to introduce Will Fawcett and Amelia Drew, both joined Homerton looking at physics from their different angles in the last few years. Will is a research associate and Amelia, a junior research fellow who joined us, if I remember right, Amelia, just as the world was going into lockdown. And some of us in Homerton have had the pleasure of meeting Amelia in 3D for the very first time over the last few weeks. So Will and Amelia will be examining whether the great discovery in the physical world that was announced in the media this year bears scrutiny, and whether the world of physics has been rocked to its core or not. Will, over to you.
Thank you very much. Okay, I'll just share my slides. Could you just confirm that you can see that?
Yes, we can. Okay,
great. So yes, thank you everyone for coming this evening. Yeah, let's get started. So earlier this year at the Fermi National Accelerator in the United States, an announcement was made. They found that some charged particles wobbled more than expected whilst going round a magnetized ring. Now, this may sound innocent enough, but the result has the potential to shake physics to the very core. It could mean that there is an entirely new force of nature which could help our understanding of how the universe works in the most fundamental way. And if you listen to this presentation, we'll tell you more about how this was done and what it can mean. I'm William Fawcett. I'm a Director of Studies in Physics at Homerton, as well as a particle physicist with the Cavendish Lab. I spend my time between Cambridge and CERN, where I work on the ATLAS experiment at the Large Hadron Collider, a massive particle accelerator underneath the French-Swiss border. And I use data from these experiments to try to discover new fundamental particles that could help explain the origins of the universe.
Yeah. And I'm Amelia Drew. I'm a theoretical cosmologist. And as Matthew said, I joined Homerton as a junior research fellow in October. I'm based in the Department for Applied Mathematics and Theoretical Physics. And broadly, theoretical cosmology is research into the universe and how it's evolving and how it began. Okay, so should we get started? Okay. So what we're going to talk about this evening is just a very fundamental question that has fascinated humankind for centuries, and that is the question of what is the universe made of? So of course, this appeals to our very nature as humans to understand what makes up our universe. And as a result of this as well, this is one of the driving questions behind a lot of the research that goes on into particle physics, cosmology, and other physics research. Yes, so we're going to sort of drill down into what could make up the fabric of our universe. Okay. So one of the first real models that we know about of the composition of our universe was proposed by the ancient Greeks in around 2,000 to 3,000 years ago. And they thought that everything on the Earth was made up of 4 elements: earth, water, air, and fire. Now, this is a very attractive model. However, we know that this is incorrect, as our world is a lot more complicated than this. However, one of the key points of this model that they believed was that it was fundamental in that you can't transform between the 4 different elements. So this is something that we're looking for in our model of the universe. If we move forward to around 1800, much more sophisticated models begin to emerge. So you may recognize this from school chemistry. This is called the periodic table of the elements. And this was developed by a Russian chemist called Dmitry Mendeleev. And what we have here is a table of all of the what was believed to be fundamental elements at the time. And the important thing here is the structure that we see. So we can see that, for example, all the elements in certain columns have certain scientific properties. And this structure was predictive, such that actually Mendeleev was able to predict the existence of certain elements before they were actually observed. However, we know that although this provides us with some predictive power, which is useful, again, this is not fundamental, as we can actually still transform between these elements via processes such as radioactive decay. So if we now move forward to the 1900s, this is where we begin to even drill down further into the fundamental properties of these elements, and we come up with the model of the atom. So again, this is something that a lot of people will be familiar with. And we have the nucleus here with protons and neutrons in the center and electrons orbiting around the outside. And each of the elements in the periodic table previously have a different number of protons in their nucleus. And then if we then drill down even further to the 1960s, we get the discovery of quarks, which make up the protons and neutrons within the nucleus. So we can see here that we're drilling down to smaller and smaller particles. So is this it? You know, if we keep going smaller and smaller, with the quarks and the electrons, are we now as fundamental as we can go? Well, this is where we need to start asking the question, what's holding all these particles together? So why are the electrons orbiting around the nucleus like this? Why are the quarks all stuck together? And this is where we need to start introducing the concept of a force. So if we move to the next slide, a lot of you will be familiar with the electromagnetic force, which is responsible for the attraction between positive and negatively charged particles. You may be less aware of these in your day-to-day lives, but two other forces that particle physicists are aware of are the weak force and the strong force. And the weak force is to do, governs physical processes such as radioactive decay. And the strong force is responsible for example, holding atomic nuclei together. So if you've ever thought about the concept of a force in any kind of detail, you may think of it as some kind of action, spooky kind of action at a distance where, you know, something is causing a positive and a negative charge to come together. But in fact, what's really happening is that these forces are mediated by other types of particles. So what we see, if we just move on to the next slide, is that each of these forces is associated with a particle that mediates the force. So some of you may have heard of the photon, which is associated with the electromagnetic fields, but there are equivalent particles as well that mediate the weak force and the strong force. So the weak force particles are called the W and Z particles, and the strong force is mediated by the gluon. So now if we move on to, yeah. So what we have on this slide, if you just ignore everything that's not in the red circles for the moment, on the right-hand side, we have the force particles, which I outlined before. And then we have also circled the up quark and the down quark, which made up the protons and the neutrons in the atom, in the model of the atom previously, and the electron circled as well, which was orbiting around the atomic nucleus. So you may think now, okay, so we've got our particles that make up the atom, we've got the forces that are keeping them in place. Is this it now? Well, you may guess from the presence of other particles on this slide that in fact, of course, this isn't the case. And what's actually happened is over the last few decades in particle physics experiments, observations have been made which are not consistent with just having these two quarks and the electron and just these force particles. And in fact, in order to explain our observations, we actually have two extra generations, so-called, of quarks and electrons. So we have here, they're called the charm and the strange quark, for example, a couple of others, and then two more generations of electrons. And in addition to this, we also have the Higgs boson. So this is a sort of a buzzword particle that a lot of people will have heard of in the news. Around 10 years ago, it was discovered, and it's responsible for giving the particles mass. So this is known, all the particles together on this slide, as the standard model of particle physics. And it's an incredibly successful model because it's provided us with incredibly accurate and precise predictions of properties of these particles, which have been measured and confirmed by experiment. Okay, so we have the standard model. On to the next slide, please. Yes. So, as a brief interlude from technical details, the late Stephen Hawking said that somebody told him that each equation that he included in his book, A Brief History of Time, would halve the sales of his book. And he said he did put in one equation, Einstein's famous E equals mc squared, and he said he hoped this will not scare off half of his potential readers. So what we have on the next slide is our equivalent to this. So on this slide, this equation is the equation of the standard model. So this expression contains all of the physics in the standard model, and it's really remarkable that it can just be written down on one page. Granted, it is complex, but yeah, it's a really remarkable achievement of physics, of theoretical physics. Okay, so we've got our standard model. Is this it now? We've had all these particles, we've explained everything that we think we see, but in fact, no, there are some quite large, some quite significant observations that aren't explained by the standard model. And this is related sort of to what I do in terms of theoretical cosmology. And to see them, we have to zoom out from the tiny scales of the particles all the way out to the large scale of the entire universe. So the first problem that we see is when we look out into our universe, we can see, for example, the galaxies that are shining, the light comes to our eyes and our detectors, and we can see the galaxies out there. And we can also detect other types of matter by other types of radiation. And by doing this and mapping the whole sky, we can work out how much matter there is out there. However, there's another way of detecting the amount of matter that we see, and this is via gravity, an effect that's known as lensing. So Einstein's theory of general relativity says that if we have some heavy mass, if we put some light behind it between the mass and an observer, the light will actually bend around the massive object before it hits our eyes or our detectors. And so what we see here on this slide is an example of this. So what we have with the arrows pointing here are actually one galaxy. So what's happened here is there's a galaxy that's behind the central galaxy, and the mass of the central galaxy has bent the light from the one behind. So it now appears as two separate things on the side. So it's like now gone round and it is hitting our detectors on the other side. And if we then work backwards, if we measure the amount of lensing that there is, we can determine via that theory how much mass there must be between us and the distant source. And if we then compare the measurements with the radiation that I talked about first versus the gravity measurements, we get a mismatch, and we see that the amount of mass that's predicted by gravity is higher than what we actually see directly. If we move on as well to the next slide, some slightly more direct evidence for this, and it's seen as being some of the most convincing evidence, is known as the bullet cluster. So what this is here is two clusters of galaxies that are moving through each other. And via the measurements that I talked about before, we can determine that there's a clump of ordinary matter, which is in pink on the slide. And then in purple, we have what's known as dark matter. So the matter that makes up the extra portion from the gravity is termed by physicists as dark matter. So it turns out that of the matter that we think we understand, if we actually look out there, there's 85% extra that we don't know what it's made up of, and it's not encompassed in the standard model. So if we now move on, we have a further problem, which is the problem of dark energy. So what this is we're able to measure distant galaxies via our detectors, and we can see that galaxies are accelerating away from us in a faster and faster manner, which indicates that the universe itself is actually accelerating in an increasing way. And what this means is that there must be, there must be something else there that's driving this expansion. And what we see, in fact, is that, okay, so this expansion is driven by something that is incorporated into Einstein's theory. However, if it's calculated directly by particle physicists, if they calculate the energy that should be in the vacuum, it's called, there's a huge discrepancy between the particle physicists' calculation and the gravitational calculation. So again, not only now do we not know what the vast majority of the matter is actually made up of, if we actually take the entire energy density of the universe, about almost 3/4 of it, again, we don't know what is causing this expansion. Okay. So next, we have a problem of antimatter. So what we see in our particle physics detectors when we perform experiments is that whenever a particle of matter is created, a particle of antimatter is also created. And these out of the if this happens out of the vacuum, and then when these come back together, they'll annihilate and again leave just a vacuum. However, we're here now, the universe is here, we see matter, okay? So not all the matter and antimatter could have annihilated in the early universe. So as it says here, for every billion ordinary particles annihilating with antimatter in the early universe, 1 extra is left standing. So we don't know again now what caused this asymmetry, what caused more matter to be made than antimatter, and what has resulted in us now being here. And finally, we have one more problem, which is, why is the standard model structured as it is? We've got this model, it describes everything incredibly precisely, but we have all these properties. So we have 3 different generations of quarks and leptons, like I said, and they all have very specific properties. The charges, the electric charges exactly balance each other. So why is this the model that's the right one? Is there some underlying reason, or is it just by chance? Is it just that's what happens to be there? And also within the standard model, there's a huge thing that's missing, which is, if we go to the next slide, the force of gravity. So I spoke about the electromagnetic force, the weak force and the strong force, but I didn't mention gravity at all in the standard model. So this somehow needs to be incorporated. Okay.
So it seems that we're at a bit of an impasse here. All the measurements that we make in particle physics tell us that the standard model is right. But hopefully Amelia has convinced you that there's so many glaring problems with the standard model that there must be something else out there. So the question is now, where do we go from here? Well, until recently, actually, we weren't sure what to do. But quantum mechanics offers us this one weird trick. This might sound ridiculous, but pairs of particles can spontaneously appear and disappear out of the vacuum. This indeed violates the conservation of energy, but only for a very short time. And this effect is so small, it would be impossible for you or me to notice. But we do know that this effect happens for the particles that we've already discovered, those particles in the standard model. But we also suspect this might happen for particles we haven't discovered yet. So if only we could somehow measure the effect of these so-called virtual particles, we might be able to discover a new particle via this effect. And this is exactly what the physicists at the Fermi National Laboratory in the United States set out to do. This is a picture of their research lab. As you can tell from its strange shape, it's inhabited by physicists. So for all its flaws, I want to come back to the standard model. And I want to focus on these 3 particles in the red box in the lower left. These are called the charged leptons. And there are 3 of these charged leptons, the electron, which you may have heard of, the muon, and the tau. The muon is pretty much a heavier version of the electron, and the tau is a heavier version of the muon. Apart from their masses, all the properties are almost identical. But one thing that's important is that the heavier a particle is, the more likely it is to interact with these virtual particles. But there's a price we pay for this interaction, and that price is stability. The heavier a particle becomes, the less stable it becomes. And the muon is kind of in a Goldilocks zone. It's not too light like the electron, so that it's impossible to measure the effect of these virtual particles. It's also not too heavy like the tau, so that it decays too quickly, so we can't really get a handle on it. However, the muon's lifetime is only about 2.2 microseconds. So we need to use another trick from special relativity called time dilation. And if you speed these muons up very fast relative to us, it appears as though they live longer. And this allows us to make the measurements that we need. And so this is exactly what the Fermilab scientists did. I don't know if you can see my mouse, but this is a picture of their experimental setup. There's an injector here, which injects muons into this blue ring, and muons are then spun around it. So here you can just see an animation of that. Muons are being injected into a ring. They're spun around this ring, and a magnetic field is applied to these muons. And so what happens to the muons while they're in this magnetic field? Well, they start spinning around. And you can see that in this animation that some virtual particles appear out of the vacuum, and they cause these muons to wobble a little bit. And this tiny effect of the wobbling is the effect that the Fermilab scientists have measured. And here's their result. It's called the muon's G factor. If it wasn't for these virtual particles appearing out of the vacuum, this number G would be exactly 2. But you can see it isn't. And so this effect is real. But you can also see that there's 2 numbers here. There's the theoretical prediction at the top and the experimental result at the bottom. You can see that these 2 numbers are slightly different. And this may mean, the fact that these are different may mean that there is a presence of a particle that we haven't incorporated into our theory of the standard model. So in other words, there may be something else that we haven't discovered yet, causing extra wobbling. So before I want to go on, I just want to actually mention the precision on these numbers. You can see that there's many decimal places here. And this is, in fact, one of the most precise measurements ever made. It's truly astonishing. It's like measuring the length of a football field to within the width of a human hair. And so I just come back to this picture. The fact that I mentioned that the 2 numbers are different could mean that we're measuring the effect of a yet unseen particle causing some extra wobbling. And this particle has the right properties to be a force particle, like the gluon that Amelia mentioned before, for example. And so this could be the first hint of a new fundamental force of nature. Here's the result I mentioned to you before, but in a graph form. The theoretical prediction is on the left in the green, and the experimental result is on the right. And you can see they differ from each other with a statistical significance of 4.2 sigma. This is quite a lot, but in particle physics, we require 5 sigma to claim a discovery, so we're not quite there yet. Before I go on, I do need to mention that there have been some challenges to the theoretical prediction, and it actually could be slightly closer to the experimental result. But these calculations really are on the very bleeding edge of science, and so they're extraordinarily difficult to do. So there should be some caution when interpreting these results. So what could this new particle be? Well, one possibility is that it could be a supersymmetric particle. Supersymmetry is a theory that predicts that for every particle in the standard model that we already know about, shown in the circle, there's also a so-called superpartner to it, in a similar way for that every matter particle has an antimatter counterpart. And this theory, it's a beautiful theory, it has the potential to solve a lot of problems with the standard model that Amelia mentioned earlier. In particular, it could shed light onto the mysterious nature of dark matter, and it could also help explain the structure that we see in the standard model. I really like this picture as it shows both the standard model particles that we know about in the middle, and also the supersymmetric particles in these diamonds on the outside. But to go further, it also leaves some black diamonds or unfilled diamonds that are perhaps for things that we haven't thought about yet. So how do we search for these particles directly? Well, this is where the CERN Large Hadron Collider comes in. Here's an aerial view of the complex. As I said before, the LHC is the world's largest and most powerful particle accelerator. It's 27 kilometers in perimeter. It's about 100 meters underground and spans the French-Swiss border. You can get a sense of how big it is by just looking at Lake Geneva or Geneva Airport. And there's at least 10,000 physicists working at CERN, coming from over 113 countries. And so how does this machine start? Well, it all starts with this bottle of hydrogen on the left. And the hydrogen gas is taken out of the bottle and ionized to form protons. And then these protons are transported through various machines, like you can see on the right, and given more energy and accelerated close to the speed of light. These protons are then injected into the Large Hadron Collider tunnel, which you can see a picture of here. And you can see it's this is the 27-kilometer long tunnel, and you can just about see the curvature of this at the focus of the picture. And the LHC injects even more energy into these protons and gets them even closer to the speed of light. Once the protons are inside the LHC tunnel, they're brought to collision at 4 different points. Around each of these points, we build a detector. They're called ALICE, CMS, LHCb, and ATLAS. And these are the 4 points labeled around the ring. I work on the experiment called ATLAS. And here's a picture of the ATLAS detector. It's absolutely huge. You can get a sense of the scale from the small people stood around the detector here. It's about 12 stories high. It's 46 meters long, weighs something like 7,000 tons, and it takes around 5 killer physicists and engineers to maintain and operate. And what it does is it takes 160 megapixel snapshots of the particle collisions as they occur. Now, that on its own may not sound very impressive to you. Perhaps your phone cameras aren't too far away from something like that. But one of the things that this does is it takes these photos 40 million times every second, and it can survive radiation that would destroy your devices and kill a human in a few moments. So here's that animation of the proton collisions happening inside of ATLAS. You can see that there's 2 proton beams entering from each side of the detector, and they're being brought to collision in the center. And the energy of these 2 proton beams is so high that new matter can be created from these collisions. And we hope that in this new matter, there will be some new undiscovered particles that will be created. And it's our job to find them in these collisions. Just to give you another sense of scale, here's a picture of me when I went to visit the detector. On the left, you can't really get far enough away from the underground cavern. Isn't big enough for you to get far away enough to get a picture of the complete detector. So you can just see a small segment of it here, really. It's so big it even has rooms in it, and I'm in one of those rooms in the picture of the top right. And on the bottom right is a picture of a CERN vacuum cleaner, which you can wear like a backpack, and you feel like a Ghostbuster. Here's a picture of what one of those snapshots that the ATLAS detector takes. You can see some tracks that charged particles have made as they traverse through the detector here in the middle. And then these sort of rectangular shapes represent energy deposits of particles that have slammed into the side of the detector and deposited their energy while they slowed down. But with 40 million of these pictures being taken every second, it's impossible to look at all of them. And so, of course, we don't look at the pictures themselves, but we analyze the data in a statistical way. And here's an example of that. You'll see here is how we discovered the Higgs boson back in 2012. That's the particle responsible for mass. As we collect more and more data, you'll see a bump appearing in the center of this plot. And that bump corresponds to the Higgs boson. Now, back in 2012, the situation was quite different. We had quite a good idea of where to look for the Higgs boson. But now with supersymmetry and other physics, other theories of new physics, we don't know quite where to look in our data. And this is why the Fermilab result is so important, because it gives us some idea of where to look for these new particles in our data. And this combined with the power of the LHC, which gives us the how to find these new particles, could mean that we're in for an exciting future with many discoveries. And so to our last slide, this is a picture I like as an analogy for where we are in particle physics at the moment. I like to think it's as though we're on a ship in the middle of the calm sea with nothing but water in every direction. And we think there's new land out there, but we don't know what direction to sail in. This new result is like seeing what could be an island in the distance, and the LHC data is what's going to take us in that direction. So, yeah, thanks for listening. And are there any questions?
Brilliant. Thank you so much, Will and Amelia. I'm going to pretend that I understood more of that than I actually did, but just for effect. Thank you hugely. So there are some questions, and there are questions already coming in. That's terrific. My suggestion is just to make for a slightly more dynamic experience. Unless you are asking a question anonymously, I might ask if our questioners are willing to be unmuted and to ask the question live. It might make for a little more of a dynamic end to our session. So SC Kapsaskis, if you are willing to be heard, then I'm going to ask you in a moment to ask your question live and see if we can get some dialogue going with our panelists. So are you able to speak to us?
Yes, I am. Thank you very much. I hope you can hear me.
We can, perfectly. Thank you.
Good evening from Athens, Greece, in fact, where I am.
Fantastic. Great to have you.
I had a question. You mentioned dark matter in the course of your talk, and I'm rather intrigued. Every time I hear about dark matter, the suggestion is that it's something very different from what we can observe. But isn't it just possible? I mean, physically, we can only observe mass in the cosmos that actually generates light, like stars, like the sun. Whereas what I would call rocks, like the Earth and exoplanets, obviously we can only see via the jiggle they produce in stars' orbits. Couldn't it just be that this dark matter is just basically non-light emitting rocks rather than stars, rather than something more exotic?
Yeah, I can take this one. Yeah, that's a really great question. And basically, so yeah, it's it seems quite like a straightforward solution, and it's kind of encompassed in cosmology by the kind of abbreviation MACHOs, which stands for massive compact halo objects. So this is basically objects that, as you say, emit little radiation and can only be detected by the gravity methods that you talked about. But basically, I was kind of just looking, I was Googling just to get some actual numbers during Will's half of the talk. But basically, it's a bit of an unsatisfying answer, but it just doesn't, the numbers and the kind of observations just don't match up with it, with it being that. There are limitations on the mass, for example. So I think I read that there are groups that have ruled out dark matter being, this is just Wikipedia, explained by machos with a mass in the range of 1 × 10⁸ solar masses to 100 solar masses. So they've ruled out quite a big chunk anyway. And yeah, there are other observations as well that mean that they could make up a small proportion of the dark matter, but they can't explain the actual total amount that we
Right. Okay. Thank you very, very much, and congratulations. It was excellent. Thank you.
Thank you.
Super. Thank you for that. There are several questions in the chat about wobbling. So maybe you could talk to us a little. What do you mean by wobbling? How do you measure it?
Okay, perhaps I can answer this, and maybe I can go back to my slide where I show this effect. Well, so by wobbling, I suppose specifically what I mean is you can think of these muons in a magnetic field. They process in the same way that a spinning top sort of spins around an axis when you give it a lot of angular momentum. And then, you know, the wobbling is almost as if you started to push your spinning top a little bit while it was spinning around, and then it would literally wobble around a bit more. So that's the sense of what I mean by the wobble here. It's affecting the gyromagnetic ratio of the muon. And I think there's perhaps another question about how this is actually measured. With great difficulty. So I mean, they need to use this ring here. And what happens is, as the muons go around a corner, they accelerate, and charged particles, as they accelerate, emit radiation. They emit photons, and you can measure these photons very carefully. And it's from the measurements of the photons you can figure out how much the muons were wobbling. And then you can, you know, repeat this measurement billions and billions of times, and eventually you get down to the statistical significance you need to figure out, you know, exactly how much they did wobble, and infer that, you know, these new particles existed. So I hope that goes some way to answer some of your questions.
Thank you. That mops up quite a few questions on wobbling. Thank you very much, Will. I'm going to invite Rick now to ask. He has a question on the Higgs boson. Rick, are you with us?
Thank you very much. So it's a question from a non-physicist, but on the one hand, we hear that gravitational force is caused by mass and energy. And then in the quantum world, we hear that the Higgs boson is used to endow mass to particles, and then sit there wondering whether there's any relationship between the two. Or are they two ideas from conflicting theories?
Perhaps we can both answer this one, and perhaps I'll start from the particle physics perspective, and then Amelia can talk about gravity. I mean, okay, from a particle physics perspective, yes, the Higgs boson generates the mass of the fundamental particles. But there's, well, one of the problems that Amelia mentioned is that we don't have a force particle responsible for gravity. We don't have a graviton. In other words, there's no quantum theory of gravity. Well, there's lots of quantum theories of gravity. None of them work particularly well. So that's perhaps the side from the particle physics side. I don't know, Amelia, if you want to add to that.
I think you've interpreted the question differently. I think, what I got from the question was, you know, is the mass that's given to particles by the Higgs boson the same as the mass that leads to the gravitational force? I think naively I would say yes, no, because you have massive particles and then the mass of the particles leads to a gravitational force. But you're right that it's not in the standard model in the way of the particles that we were talking about before. I'm not sure.
I think this is where the word mass has probably got different meanings in different theories. So
it potentially does. I mean, there is this tricky situation where it could be the case that so-called inertial mass, which is the mass that you experience when you're trying to push something with a force, could be different from its gravitational mass. Now, there's people who've done experiments to say that these things are the same to like pretty extraordinary degrees of significance, but it's not necessarily fundamental. It's not in our theory that inertial masses need to be the same as gravitational masses. So they could be different, but our results, our experiments indicate that they are identical.
Thank you. I guess the question's still hanging there. So anyway,
yeah.
Great.
Super. Thank you for letting us explore that. I'm going to ask Ahmed Tozi now. Would you, if you're with us, would you like to join us and ask your question about the multiple components of the standard model equation?
Hi, beautiful presentation, by the way. My disclaimer is I'm a non-physicist, but I'm just trying to understand what relationship this could have to the standard model, because it seems to me it comprises different components which are based on maybe different forces, or I'm not sure how, but does this anomaly, does it correspond to a particular part of the standard model or multiple parts? And does that give us any clues as to where to look or how to look for this putative particle?
So if I've understood your question correctly, how
does it relate to the standard model, this anomaly, G-factor anomaly?
Well, it doesn't, I suppose it doesn't relate directly to the standard model in the fact that it doesn't agree with the prediction. So from the standard model, the particles that I show here and the forces that we know about that exist in the standard model, we can make this prediction of this G number. And then, we measure it, and we find that the agreement isn't there. Now, in all of our other experiments at the Large Hadron Collider, we do similar things where we, make a prediction based on the standard model, and we find that often the data matches the standard model. And the nature of the disagreement suggests that a new particle could be of the type of a force particle on the right-hand side. And indeed, we have other theories, for example, supersymmetry, where you would have more particles than you see here. And in the supersymmetric theory, you can get the correct prediction, or rather a prediction that matches the experimental results. So it seems, at least for the moment, this so-called supersymmetric theory, where you have more particles than what you see here, agrees with the experiment better than the current standard model does. But there's a saying, for extraordinary claims, we need extraordinary evidence. And to rule out the standard model would certainly be an extraordinary claim. So we don't have enough evidence to do that yet.
Thank you.
Great. Thank you, Ahmed. I'm going to go to John Mason. John, would you like to join us and ask your question? There you are, John. Hi.
Hi there. Yes, in fact, the last question you sort of probably answered what I was going to ask, because I was going to ask whether or not the new particle, the new evidence was going to give you an insight into the possible supersymmetry particle itself. So as I was understanding it, the supersymmetry models would have a whole series of new particles, and whether or not there was one specific one of those, or one of the force mediating ones, that you would be able to identify as the particle that was being observed.
Well, from the Fermi Lab result, we couldn't say for sure. However, because it's a sort of indirect measurement, and we need the Large Hadron Collider to make the direct measurement. However, it could be the supersymmetric particle to the muon, which is called the smuon. I mean, that would make sense because the properties of the smuon and the muon are related, and we've made measurements relating to the muon. And so theories of supersymmetry, where you have a smuon that's around less than 4 times the mass of the Higgs boson, give you the experimental result of this G-2. So in fact, that is something that we are currently looking for. We are looking for the supersymmetric partner of the muon. And actually, this has redirected some of our efforts to start looking specifically for that since this G-2 result has come out from Fermilab.
And I presume if you did indeed identify that, that would then say, because that would nail down some of the parameters maybe in the model, that would then point you to somewhere else to look for the next one. Is that right?
Exactly, yeah. So it could potentially be quite exciting. Unfortunately, with the LHC, again, we might be able to sort of discover, we've got a particle that looks like this muon, but probably we would then need to build an even bigger hadron collider to really nail it down, because it must be very heavy. And plans are afoot to actually build a 100-kilometer collider. So yeah, keep paying your taxes.
Thank you.
Terrific. A good message for everybody these days. Well done. So we have a question from Neil Dunlop, but it's a quick and dirty question. Let me see if I can ask it quickly. Is there any indication of how long the LHC experiment will have to run for if the new particle is to be resolved?
That's a good question. I mean, currently the LHC lifetime, I mean, for the current experiments, we still have a few decades left of experiments to run. It really depends on how heavy that, let's just run with it that a muon exists, the supersymmetric particle of the muon. If we were to get some evidence for that, how long it takes to get enough evidence just depends on how heavy it is. And of course, we don't know. We have no knowledge of the particles that exist beyond the standard model. So, we really can't say. Yeah, in a sense, we're on that. We're still on this boat in the middle of the flat ocean, and we can't really see, where to go apart from this new hint.
So keep paying your taxes. Right. So there are a few. I'm conscious we haven't worked Amelia very hard in this Q&A. I think we probably ought to.
That's okay.
Amelia, we have a few questions from anonymous attendees who.
Yeah, I think that one at the top is one I can probably answer.
See if you
yeah, I can read it out. I don't know who's asked it, but it says, could it be that types of matter are not within physics but additional to physics? Is the search using physics with its less than full explanation suggesting the matter is not representable by physics? Matter is so tangible, it is possibly an area of existence as an extension of chemistry outside the atomic structure. Yeah. So basically, I think this is a really good question, because it's basically asking, it's kind of drilling down into the whole crux of the problem, which is that we have this dark matter, and the whole reason that we don't know what it is that it doesn't interact with the matter that we know, which is exactly what you've said. And the only way we can detect it, as I was talking about before, is via its interaction with gravity. So this may be because we haven't included gravity in the standard model. But I think what you're saying is basically, how can we hope to detect it at all within our current models, because it might be something that's not even accessible to theory. And that's always, that's always a possibility. There could be stuff out there that we can't describe, that physics it's not possible to describe. But efforts are out there at the moment to try and find dark matter by direct detection methods. But of course, these are incredibly difficult because you've never directly detected any of these dark matter particles. So it's very, basically they'd have to sort of decay into real matter particles via some mechanisms that we don't know, and then we'd have to be able to detect those specific reactions and things like that. So that's a potential way if they were to decay, or to decay into matter particles, or matter particles were to decay into dark matter particles somehow. That might be a way that we might be able to detect them directly. But yeah, this is one of the primary problems at the moment in sort of dark matter searches.
Great, thank you. There's another couple of questions from anonymous attendees. One just in: would the Cambridge Centre for Mathematical Sciences be in a position to answer all of these questions, prove or disprove this new finding?
I don't know about prove or disprove, but there are certainly a lot of researchers within my group, more on the high energy physics side, that are looking into sort of different possibilities. I think there are supersymmetry researchers in my group as well, although I can't be entirely sure. I'm slightly more on the gravity side of things. But yeah, there's definitely research being done, certainly in Cambridge, but I think in my department as well, to potentially shed some light on this. But there are so many options, for different explanations. So yeah, it's quite a task.
Yeah, and we did collaborate directly with people from the Department of Applied Maths and Theoretical Physics. We actually work quite closely together on these kinds of things.
But I guess the networks that are involved in investigating these things are international networks as well, that you must be working regularly with colleagues around the world on this sort of question.
Yeah, definitely.
So I'm going to go now to David Gorsuch, who has a question on the relation of the standard model. David, can you join us?
He's muted, I think.
Yeah, so can you hear me?
We can. Hello, David. Hi. Thanks.
Hi. So I just wondered, is the standard model essentially a subset of the supersymmetry model? So if the supersymmetry model is right, does that mean the standard model is wrong, or just that it's kind of incomplete?
So yes, the standard model is a subset of supersymmetry. That in itself doesn't mean that the standard model is wrong, but we do know, the arguments that Amelia mentioned at the start, the lack of dark matter, the lack of gravity, etc., means that we do know that the standard model isn't the complete theory. So we know that the standard model is wrong, but we just don't know what the right answer is. Supersymmetry is one of many potential theoretical extensions to the standard model. It just happens to have a lot of very nice properties. For example, it can help explain this anomaly, this G-factor anomaly, and can help explain the nature of dark matter and things like that. Does that answer your question?
Yes, I guess so. Thanks.
Okay.
I would say as well that I'd be a bit more kind of positive, maybe, that I wouldn't say the standard model is wrong. I would basically more agree with your question that it's incomplete, because it's clearly not wrong, because it gives us such incredibly accurate predictions. But yeah, certainly everything that I was talking about with the dark matter and dark energy and everything shows that it's incomplete.
Yeah, thank you. Yeah.
Great, thank you, David. We have a question from Samer Kurdi, and I'll try to paraphrase it. What's the progress with building a new collider? Are there plans now to build a linear collider? And what are the advantages of linear versus circular?
Right. Yeah. So I alluded to this before. There are plans afoot to build a future. Well, it's currently called the Future Circular Collider. It would be 100 kilometers long, also in Geneva, and it would extend. It would extend the Large Hadron Collider ring to, well, a much larger picture than what you can see here, and indeed you can actually see a smaller ring that's used as a pre-accelerator to the LHC, and then an even smaller ring here. So we've been doing this sort of generations of colliders getting bigger and bigger for the past 70 years or something like that. In terms of the progress of the future circular collider, I mean, at the moment it's only theoretical. In principle, it's been approved by CERN, but it will be decades before we start digging more tunnels. As for a linear collider, again, there's also plans for something called the International Linear Collider, but that's sort of, I don't know, waiting for funding from various governments. The advantage of a circular collider over a linear one is that when you inject the beams into the collider, you can reuse, as the beams go around the circle, you can reuse the instruments to inject more and more energy into them. However, at the same time, this effect that I mentioned before, charged particles, when they accelerate, when they change direction and go around in circles, they also radiate photons, so they lose energy at the same time. So you're constantly fighting between pumping more energy in and it's sort of leaking out for the ring. The linear colliders, they don't suffer from this radiation leaking out, but of course you've only got one shot in a linear collider case, so it's a bit of a toss-up between the two. And the thing that it comes down to is the mass of the thing that you're trying to collide. The heavier they are, the less they radiate. So protons are relatively heavy particles. That means we can put them in the LHC, we can spin them around in a circle and they don't radiate too much. But if we wanted to collide, for example, electrons, they're much lighter. I think they're 2,000 times lighter than a proton. And this sort of radiation effect goes to the power of 4. So electrons radiate 2,000 to the power of 4 times more than protons do when they go around a circle. So a linear collider is perhaps better for electron collisions in terms of just power.
Got it. Thank you, Will. I'm going to ask Rashid Zuberi now, who has a question on gravity. Rashid, would you like to join us? Unmute yourself.
Hi there. Can you hear me?
We can.
Hi, Amelia. Well, thank you very much for that talk. I was at CERN nearly 30 years ago, but this is very exciting and something that I've always thought to myself, the incorporation of gravity into the standard model and all the excitement with regards, LIGO and the gravitational waves. But then surely, if there are gravitational waves and wave-particle duality, there has to be a graviton. So your sort of views on that?
I don't know if I'm in any particular camp in this respect, to be honest. I mean, yeah, I'm pretty much, I don't work directly on the standard model, so I don't really have a preference over which theory I think is the right one. But yeah, I know that it is, a very popular opinion that basically there should be a graviton, and this is what we'd expect to see. I don't know if Will has.
Yeah, I'm not sure if I can add a great deal. Should supersymmetry exist, there could be a supersymmetric partner to the graviton, which may be easier to actually experimentally find. So we may discover a supersymmetric graviton before the real one, but of course that's all hypothetical. In terms of experiments, discovering the graviton certainly wouldn't be possible with the LHC. It would have to have a very small mass. It would interact too weakly for us to be able to find it. Sorry, I didn't mean it needed to have a small mass. It would interact too weakly for our experiments.
Thank you.
Great, thank you for that. I think we have time for one final question, and I'm going to ask it. It comes from Roger Richardson, who asks a very short question, which to my untutored eye looks like it might require a 3-hour answer, but let's see what happens. Where do we stand now as regards string theory?
Does Will want to? I don't know. I can say Yeah, I don't, again, this is not very helpful because I keep just saying I don't do things, but I don't do string theory. But I have been to a lot of talks which refer to something called the swampland, which is kind of a lot of different field theories that may include string theory, may not. And there's a lot of work going into like narrowing down all the possible field theories. So I don't think any huge progress has been made in terms of determining whether string theory is right or wrong recently that I know of.
Yeah, I think string theory is still too far away from experiment to for us to be able to make an actual statement on it. Supersymmetry can be, part of string theory or derived from string theory, but again, we don't even have any evidence for that. So, yeah.
I think the energy scales for string theory are still completely out of reach at the moment to experiments, as far as I'm aware.
Okay, all right, thank you. Now, at something like 6:59 and 30 seconds, somebody asked a question, so I think we're probably going to allow it. This is the definitive last question, and it's come up in the chat. Useful always to see if you can define boundaries. Is the speed of light still a theoretical barrier? Is there a maximum density, stroke gravity of an object? Is there a maximum temperature? Is there a maximum frequency of electromagnetic radiation? In other words, are there ceilings on these possibilities?
Yeah, I can answer some of that. So yeah, the speed of light has withstood all tests. I mean, actually, so the speed of light is also equivalent to the speed of gravitational waves. And it's measuring the speed of gravitational waves to be consistent with the speed of light that has actually disproven a lot of alternative theories of gravity. So every measurement that we've made of the speed of light and the speed of gravitational waves is still consistent with the value that we've always known. Is there a maximum density of an object? I mean, the densest object is a black hole, which I guess technically has sort of infinite density at the center because it's a singularity. I don't know if that's what you were talking about there. Maximum gravity of an object, again, that would be a black hole, but I think there might be an upper limit on the size of a black hole, but that might be determined by the age of the universe rather than anything else. Maximum temperature, I don't know. I don't think so. Maximum frequency of EM radiation. I mean, I don't think there's a maximum frequency in theory. I don't know. Does Will have any more? Because you can just go up to higher and higher frequencies of gamma radiation. I'm not aware of there being a maximum, but I might be wrong.
Yeah, I mean, there is this idea of, you've probably heard of absolute zero, but there is an idea of an absolute hot as well, and I think that's sort of predicated on the idea that there's a Planck distance, this minimum distance scale. But these kinds of things again are, let's say, theoretical ideas as opposed to being concrete laws at the moment. And again, yeah, I don't know if there is a maximum frequency of EM radiation, but we have measured at the very least particles with energies of peta electron volts. So this is 10 to the 15 electron volts. So these energies of these particles that we get from outer space are, far beyond what we can create in even our most powerful colliders. Orders and orders of magnitude higher energy than we can create, and at the very least, these super high energy cosmic rays would have incredibly, huge frequencies. And in fact, we don't know we don't actually know what creates such high energy particles. But if there's anyone ever worried about the LHC, creating black holes and destroying the world, then we get showered by much higher energy particles than we can create. So sorry, I don't know. it doesn't seem like there's a limit to how much energy you can add to a particle, but again, yeah, I don't know if there is a maximum.
Fantastic. Thank you very much, Amelia and Will. Thank you for reassuring us that the LHC isn't going to end the world. And thank you for a fabulous presentation. I think you've been able to see something in the chat of appreciation from your audience. Thank you to our audience for bearing with us. Those of you who were with us before 6 o'clock witnessed a slight technical panic on our part, but we got underway very quickly. And again, thank you hugely to our presenters. I owe you a pint. Thank you, everyone.
Yeah, thanks, everyone.
Thank you.